Hello everyone and welcome into yet another live stream. And hi there everyone, you're about to go to school, why start the streams early? Well, that's because this is a special live stream. I don't know, that's just the only time of day I'm free. Hi there. Music is a bit loud. There we go. Much better. See ya other side. See ya. Sorry about that, but unfortunately this is the only time of the day that I was free for today. Actually, maybe late at night, but I don't want to start this stream late at night. We know why? Because this is finally we skipped over a couple of chapters because apparently they weren't all that important, but there we go. Introduction to semiconductors. And then from there we have dope semiconductors, then we have, oh, that's really short. That's a really short chapter. That's good. Welcome to Make It No Stream Schedule. Yeah, we don't do those. Maybe in the future. Maybe once, you know, it will become an actual full-time job for me. Maybe then. But for now, we just stream whenever there's time. Anyhow, you know what time it is, right? Oh, introduction to semiconductors. Most of this information is irrelevant. I call it redundancy. Alrighty then. If you only had to worry about simple conductors, life would not be very complicated. But on the other hand, we wouldn't be able to make computers, cell phones, and a lot of other things which we found to be useful. We will now move on and talk about another class of conductors called semiconductors. Okay, so we have resistors which resist, conductors which conduct, and semiconductors which are weird. Got it. Cool. Neat. In order to understand semiconductors and in fact get a more accurate picture of how metals or normal conductors actually work, we really have to resort to quantum mechanics. For fuck's sake, no. Why? Every single... What? It's... Every single stream. Always. The same thing. The same precise thing. Why? Why always quantum mechanics? Why? Why always quantum mechanics? Electrons in a solid are very tiny objects, and it turns out that when things get small enough, they no longer exactly follow the classical Newtonian laws of physics that we are all familiar with experience. Yes, this is not the purpose of this course. Teach you quantum mechanics, thank goodness. Minecraft Redstone. Yeah, this is you know, the same level of advancement, I'd say. Okay, so what we're going to do instead of describe results, which we're looking... Okay, cool. Fortunately, we already know the quantum mechanics, because we've been over this multiple times. Solids, and these are the ones we will be talking about, especially semiconductors, are crystalline materials, which means that they have their atoms arranged in an ordered fashion. We can take silicon, the most important semiconductor, as an example. Silicon is a group 4 element, which means that it has 4 electrons in its outer or valence shell. Silicon crystallizes in a structure called diamond crystal lattice. This is shown in figure 3321. Each silicon atom has 4 covalent bonds arranged in tetrahedral formation about the atom center. Oh, remember that. Well, I don't have it copied, but just yeah, a while back in the chapter there was, you know, what do you expect when researching light? No, this isn't light yet. I mean, no, not yet. I don't think we'll get light. This is computers. Well, kind of good enough. In 2 dimensions, we can schematically represent a piece of single crystal silicon as shown in figure 3322. Each silicon atom shares 4 valence electrons from 4 nearest neighbors. Brick structure, okay. The outer shells of all of the atoms blend together and form what is called a band. The electrons are now... Okay, so band is like a... Hey, is knowledge technically dimension 0? I don't... What? Wait, hold on. What? Is knowledge technically dimension 0? Because this is nothing to do at the same time. I am so confused. Okay. What is dimension 0? Well, if you... Well, mathematically, it would be just something with no directions. As in... but no, not redirections. If To simplify, it would be something with no numbers. So like if you have something in one dimension, one-dimensional object which would just have one number describing its, let's call it something you can bind to position, then zero-dimensional would have, well, a point. That would be zero-dimensional. So if you have a line, you have its length. So you can describe a line as, you know, one-dimensional thing. Mate, we're getting off track, you know? Something with no direction. Hungry, you really gotta stop with the you know, negativity. You really, mate, just come on now. Why be so negative? I don't get it. What's the point? This is not a complete story, however, for it turns out that due to quantum mechanical effect, there is not just one band which holds electrons, but several of them. What will follow is a very qualitative picture of how the electrons are distributed when they are in periodic solids. And there are necessarily some details which we will be forced to gloss over, thank goodness. On the other hand, this will give you a pretty good picture of what's going on and may enable you to have some understanding of how semiconductor really works. Electrons are not only distributed through the solid crystal spatially, but they also have distribution of energy as well. Cool. Potential energy function within the solid is periodic in nature. Potential function comes from the positively charged atomic nuclei, which are arranged in a crystal array. A detailed analysis of how electron wave function in mathematical abstraction, which one must use to describe how small quantum mechanical objects behave when for this really cool. We're not going back to wave functions, you know. The point is zero dimension, yes, because you know it's well depends. Well, hold on. Point is zero dimensional, as in when you describe the size. If you're trying to describe the size of a mathematical point, it's zero dimensional because there is no size to speak of. When you have a line, you can describe the length of a line as one dimension because, you know, it's just a single value, length. When you have some sort of, I don't know, square on a plane, you can describe its width and length, so you have two numbers, hence two-dimensional. When it comes to the point, you have no numbers, so zero-dimensional. Like a singularity. Yes. Well, mathematical point, well, yeah. Yes. It's just not like it's like a singularity. No, it's the other way. Singularity is like a point. So the definition for... Not the definition. So singularity... Physical singularity, right? The physical concept of a singularity comes from the mathematical idea of a point, not the other way around. So what can you describe the knowledge as? It's, oh mate, I'm only starting the work on the information video. You'll have to wait a couple of months for that. Not just the ability or idea to control and manipulate information ideas. Yeah, but that's high abstract definition. We could do better. Alright. Gee whiz, it's gonna be fun. Is knowledge technically dimension zero? Is kind of that question is kind of like asking a question of, I don't know, is chair technically a 7? Like, it doesn't really make sense. We are not high enough for philosophical questions. It's not really a philosophical question. No, a philosophical question would look like this. If you have a chair, how much of the material from this chair can you take away until it's no longer a chair? That's a philosophical question. That question makes sense. And it leads to, you know, continuous question and stuff, all the nasty stuffs. But the question of, is knowledge actually technically dimension zero? That's, in my opinion, that question just doesn't make sense. It's kind of like, it really is kind of like asking, is Apple a 6? Dimensions more like high abstraction levels, no they're not. Dimensions well, in the mathematical sense, dimensions just tell you how many numbers you're working with, but since we use math to do almost all of science, it kind of spills over into everything. I'm a 10 actually. There we go! Hell yeah! That's the way! Up top, mate. Boats with plank or plank to a new boat. That's called Thesis. The ship of Thesis, I think. That's what it's called. Yeah, those are philosophical questions. But I just don't get the knowledge to dimensions. Because I don't really see anything linking them. Where were we? Oh yeah, right. Bands. That's right. Electrons. Okay. Thirsty. Oh goody, there is a lot of text. Hold on, let me just move the day more into the corner. Thirsty. Unlike the case for free electrons in a periodic solid, electrons are not free to take on any energy value they wish. That's why we have gaps. They are forced into specific energy levels called allowed states, which are represented by the caps in the figure. The allowed states are not distributed uniformly in energy either. They are grouped into specific configurations called energy bands. That's what bands outlined at last live stream. There are no allowed levels at zero, pointing at zero energy, and for some distance above that. Moving up from zero energy, then we encounter the first energy band. So right here, we have a band, then we have a gap, we have a band. So everything kind of simple. Well, technically, knowledge can measure all dimensions. Yes. Sorry for the tracking you. No. That's what chat is there for, right? It's listen. If I didn't want to be distracted, I would just wouldn't get distracted. The point of these live streams is to chat. I use it as my socializing time, like the dirty socialist I am. Let's go on and on. Then you give as much balance. Okay. So all makes sense so far, right? Electrons can only have certain discrete energy levels, and so that means that electrons can only have these energy levels or these ones. If an electron has energy level like this, it's not allowed because this quantum mechanics. I missed so many of it. It feels like I fell asleep in class and woke up to integrals. To be fair, the things you've missed are mostly irrelevant. 90% of this will not be on the test. But knowledge has to take form in your neurons for you to be able to think about it. That's my issue with knowledge. Knowledge is very vague. It requires a lot of abstraction. That's why I prefer to talk about information. Because information is, information is more tangible. Information is a bit easier to define with low abstraction. It, where n is the total number of atoms in the particular crystal sample we are talking about. Okay. Interesting. Hold on, this sounds like an interesting piece of information. Each band has exactly 2n allowed states. Get it? Is the total number of atoms in the particular crystal sample. Wait, is it for silicon or for all of them? Allowed states. So allowed states being these energy levels, which means the... Wait, is it... No. This is just N. This is just standard good old-fashioned N. Alright, since there are 10 caps in the gave much represent crystal, which is 5 atoms in it. Not a very big crystal although. Okay, but is it for all crystals or just silicon? Into these bands, we must now distribute all of the valence electrons associated with the atoms, with the restriction that we can only put one electron into each allowed state. This is the result of something called Pauli exclusion principle. Since in the case of silicon there are 4 valence electrons per atom, we would just fill up the first 2 bands, and the next would be empty. If we make the logical assumption that the electron will fill the levels with the lowest energy first and only go high levels are filled. Okay, so makes sense. 2n, so basically take the number of allowed states divided by 2, you get the number of atoms in a crystal. Then, in this case, silicon has 4 valence atoms. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. 3 times 4, that's 12, plus 4 plus 4, that's... we have 20. We have 20 allowed states, and we divide it by 2, so which means this is 10 silicon atoms, And since they have 4 valence electrons each, that gives us 40 valence electrons, which means that if... Oh wait, no, allowed states per band, right? Each band. Okay, so we have 5 atoms, which means they would fill in 4 bands. Is it... Okay, I feel like I should go a bit more in depth to explain. You know what? Yeah, let's do that. I feel like it's a good idea. Copy image. So, paint. Alright. Feel special. There are better ways to feel special than good band, honestly. Okay, so here's the deal. Right here, you can see we have 1, 2, 3... Okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 allowed states. Let's call it A. Alright? Allowed states are equal to 10. Sorry for white mode, but the picture's in white, so you know. We have 10 allowed states. Now, since allowed states are equal to 2n, we know that if we divide both sides by 2, 10 is equal to 2n. Divide both sides by 2, we get 5 is equal to n. So we have 5 atoms. Does that make sense so far? I really hope so. Now, when it comes to silicon, I think it's Si. I'm 75% certain it's Si for silicon. When it comes to silicon, it has 4 valence electrons, which means we multiply the number of atoms times the number of valence electrons each has, and we get 20 valence electrons. So all of them have 20 valence electrons combined. Silicon is QX. There is no way it's QX. A guy quit joshing around. So 20 valence electrons. Now, since each band has 10 allowed states, this would mean that these can fill in 2 bands. Yes, right? Am I correct or am I wrong? Let's see. I have a memory of a goldfish, so there wasn't a... just fill up the first 2 bands. Okay, yeah, I have a memory of a goldfish, so... It's very convenient because I can read something and then I can rediscover it myself immediately because I just forget the answer. Let me just check. Well, that's not ptable. ptable.com. Wait, I can just look for silicon. Silicon is Si! I knew it! Oh, I'm smart. Oh, so make it. Pansexual means you just you don't have a problem with trans people. Bisexuality is for people who like male and female. I'm trying to... What is so the ones about? No, yeah, I get it. So, bisexual, you like male and female. Pansexual means you don't care. It's just more fun. Okay. Here we... Okay, so there we go. That makes sense. Here we have represented electrons as small black balls with a minus sign on them. So this. Yes, they fill in 2. Makes sense. Indeed, the first 2 bands are completely full and the next is empty. What will happen if we apply an electric field to the sample of silicon? Remember that the diagram we have at hand right now is an energy-based one. We are showing how electrons are distributed in energy, not how they are arranged spatially. Makes sense. On this diagram, we cannot show how they will move about, but only how they will change their energy as a result of the applied field. The electric field will exert a force on the electrons and attempt to accelerate them. If the electrons are accelerated, then they must increase their kinetic energy. Unfortunately, there are no empty allowed states in either band. An electron would have to jump all the way up into the next empty band in order to take on more energy. In silicon, the gap between top highest is 1.1 EV. There's a free powerful distance over... Oh, that's a lot of information. Free path or distance over which an electron would normally move before it suffers a collision is about 30 nanometers. And so you would need a very large electric field, several hundreds of thousands of volts per centimeter, in order for the electron to pick up enough energy to jump the gap. Okay, so silicon by itself is not a great conductor. It's more like a resistor, I would even say. Some semiconductor. Okay, makes sense. All right. Some semiconductors, such as gallium arsenide, are such poor conductors that very pure materials is sometimes called semi-insulating. Insulators such as quartz, crystalline silicon dioxide, or diamond, crystalline carbon, have had such large band gaps that it's extremely rare for an electron to gain energy to jump the gap. So far, all makes sense. What is electronegativity? It's when basically the ability to attract electrons. Basically. Kind of. Yeah, that's what it is. Omega, the only thing I remember from resistors. We haven't even gotten to them yet. A metal is an element with very small band gap, or even overlapping bands. In effect, a metal ends up with an upper band which is partially full of electrons. This is illustrated in the figure this. Here we can see that one band is full and the next is just half full. This would be a situation for the... Okay, so this would be a conductor, right? For group 3 element aluminum, for instance. If we apply an electric field to these carriers, those near the top of the distribution can indeed move into higher energy levels by acquiring small kinetic energy of motion and easily move from one place to the next. In reality, the whole situation is a bit more complex than we have shown here, but it's not too far. Okay, so, alright, so basically, if they need to jump the band, then the larger the band, the more insulating it is, because the more energy is required to actually jump the band. If there is no band gap, I should mention, gap. If there is no gap, then they can just move around freely. Go back to our silicon example. If there are no places for electrons to move into, then how does silicon work as a semiconductor? Well, in the first place, it turns out that not all of the electrons are in the bottom two bands. In silicon, unlike say quartz or diamond, the band gap between the topmost full band and the next empty one is not so large, as we mentioned above. It's only about 1.1 electrovolts. Electrovolts? I think electrovolts. And this video about how it's possible to make blue LEDs. I wonder if I should click it. Oh, that's video about that's Veritasium's video, I think. I haven't seen it. So long as silicon is not absolute zero temperature. Some electrons near the top of the full band can acquire enough thermal energy so they can hop the gap and end up in the upper band called the conduction band. Situation is shown in this figure. Okay, so if the band gap isn't too large, they can hide the spiral. Welcome. Alright, the more gaps we have, the larger the gaps, the more insulating material becomes. The less gap, the smaller the gaps, the more conductive it is. Makes sense. Silicon at room temperature, roughly 10 to the 10th electrons per cubic centimeter, are thermally excited across the band gap at any one time. Should be noted that the excitation process is a continuous one. Electrons are being excited across the band, then they fall back down to empty spots in the lower band. Each cubic centimeter... Wait, cubic centimeter? Why cubic centimeter? Doesn't matter. A cubic centimeter of silicon is what you will find at any given instant. Now, 10 billion electrons per cubic centimeter seems like a lot of electrons, but let's do simple calculation. The mobility of electrons silicon is about... Okay, we have this. We would have the resistance of 62.5 mega ohms. Okay. Alright, nope, semiconductors. I haven't drunk any coffee before this last night, I just realized. Okay, so now we're introducing impurities into the semiconductor, makes sense. So silicon is resistant enough to not let electrons jump freely, but also not resistant enough to make electrons require stupid amounts of energy. Hungry, you're spot on. Yeah, so basically you have let me just so basically you have bands, right? Let's call it B, and you have bands and then you have gaps between them. And so, hi there, Elliot. So you have bands and you have gaps between them, and basically the bigger this space, let's G blue, that doesn't make any sense. Basically, the bigger the gap, the more energy you need for the electrons to actually make the jump. Because if this one is already full of electrons, then the only place for them is right here. But in order to do that, they need this amount of energy. So basically, nothing is truly insulative if you have, you know, everything can be a conductor if you try hard enough. So yeah, I'm pretty certain every single material has a band, has infinite amount of bands. I think we read about it somewhere in this textbook already. So I'm pretty certain if you actually have enough energy on hand, I think you can use everything. Kind of tension. Don't introduce different words into it. Mate, I'm already struggling. It makes everything so weird. So it's like a dam regulating flow of electrons. It's more like a... Okay, I have one example, but I have one analogy. But it's a pretty dumb one. I have one analogy for this. So imagine you're playing a platformer, right? So you have a platform. And then you have another platform. And then here's your little guy, right? Here's your little guy. Okay? Your little guy. So this is the gap. And these are the bands. And so basically, you have your little guy. In order to actually get from this band to this band, you need a big old jump. Right? You need a big old jump. And so the larger the gap, the bigger the jump needs to be. So now imagine that you're playing this platformer, but you're playing it multiplayer with other players, and this platform is already crowded, right? It's already crowded. There's a lot of peeps. There's a lot of peeps on it, and you can't fit. You couldn't fit. You couldn't possibly fit it. I know that where there's a will, there's a way, but you couldn't possibly fit anything in there. So now what you have to do is, as your character, in order to actually fit in, you would need to be on this band, right? But you can only be on this band if your jump is high enough. This is an awful analogy, actually. I don't have a good analogy for this. Is there a good analogy for this? Hi there, Alex, by the way. Oh, Alex, you'd know. That's the best I can come up with, honestly. I mean, I'm glad to finally understand how bands work. It took me a while, and it's actually really simple. I'm kind of ashamed of just how long it took me to understand how bands work, considering just how simple they are. Oh, they really are simple. Fudge. Interesting. Yeah, precisely, you get it. Just try hard enough to make human conductor. What is a band then? Band is basically like allowed energy levels for an electron. Clear as mud, let's carry on. To see how we can make silicon a useful electronic material, we'll have to go back to its crystal structure. Suppose that somehow, and we'll talk about this, how this is done later, we could substitute a few atoms of phosphorus for some of the silicon atoms. There we go. So now we end up with... For I am busy, have a nice day. See ya, Elliot. Why is the day in all caps? It's very aggressive. It's day for once, make it... Oh, because I'm streaming like early on, actually. Oh, that's why. Okay. Yeah, it is day for once. I am actually... Yeah. First time I'm not streaming midnight. It just felt like I should start the stream a bit earlier on, because, you know, considering that this is the final electricity live stream. Because we'll get through all of this today. The mod is such a lawless land. I don't remember any moderator ever banning. Okay, the role of moderators on these streams is different. You see, I give mod to people to kind of make them stand out, you know? That's why I give mod. Not really to moderate, because there is nothing to moderate. What times do you usually stream? Well, it depends. Well... I think it's purely random. I'm pretty certain I've so far managed to stream at every single time of day possible. That's a bad reason. Why? I want to get banned. You asked for it. Not figuratively. Literally. You literally asked for it. You literally came here and asking me to ban you. That's why. No, on the stream. Yeah, on stream. Unless it wasn't you, Happy. Wait. No, it was you. Or maybe it was Sadi. That's one of you. One of y'all. Never liar. Please didn't remember that. Just, you want to come back with a different account or something? I don't know. The point is, phosphorus. We're introducing phosphorus into silicon. So, if you sneak a look at the periodic table, you will see that, ooh, always, phosphorus. Where is phosphorus? Phosphorus is next to silicon. I was learning how to count. Wait, did you get banned for that? Happy in that. Y'all are way too. No, you know what? I'm just gonna. No. I'm gonna ignore this. I'm gonna ignore this remark and we'll move on to more science. This is a respectful, actually, you know? No, daddy, saddy. Yeah, right. Okay, silicon phosphorus. Phosphorus is one element to the right, so it has 5 different valence electrons. And when it comes to bonds, I'm guessing bonds. Which is group 4 element. Okay. What this means is the phosphorus atom has 5 outer valence electrons. Wow, look at me, I'm so intelligent. Instead of the 4 which silicon has. In a lattice composed of mainly silicon, the extra electron associated with phosphorus atom has no mating electron with which it can complete a shell, and so is left loosely dangling on the phosphorus atom with a relatively low binding energy. In fact, the addition of just a little thermal energy from natural or latent heat of the crystal lattice, this electron can break free and be left to wander around the silicon crystal. In our energy band picture, we have something like what we see in figure 3332. The phosphorus atoms are represented by the added caps with P's on them. They are now allowed energy level. Now there are new allowed energy levels with. Damn it, Fetam. Oh. The dark background with bright text on it makes it really tough for me to read. For some reason, I don't know why. They are new allocated energy levels which are formed within the band gap near the bottom of the first empty band. They are new yes, okay. They are located close enough to the empty or conduction band that the electrons which they contain are easily excited up into the conduction band. There they are free to move about and contribute to the electrical conductivity of the sample. Note also, however, that since the electron has left the vicinity of the phosphorus atom, there is now one more proton than there are electrons at the atom, and hence it has net positive charge of +1q. We have represented this by putting a little plus sign on each pickup. Note that this positive charge is fixed at the side of the phosphorus atom called donor, since it donates an electron and the conduction band, but the phosphorus atom is not free to move about in the crystal. Okay, yeah. Okay. Wait, would this make a conductive material... Wait, would this make a conductive material with holes as the charge carrier? For example, I would never bad. You're gonna go through a personality. Hi there, Ramit. Welcome. Wait, so I think this would be a conductor with holes as charge carriers, right? Let's see. We need significantly change the resistance of our silicon. Suppose we wanted our 1 millimeter by 1 millimeter square to have a resistance of 1 ohm opposed to more than 60 million ohms. Turning the resistance equation, we get this. So, and hence we continue to assume an electromobility of 100 cubic squared centimeters per volt per second. We get this. So, hold on. This is the resistance equation rearranged, with both sides multiplied by sigma divided by resistance. Oh, what was sigma? Oh, damn it. 2 chapters ago we had this information, let's see. Or 3 chapters ago, actually. Right? Nah, math processing errors, my beloved. Bonding in semiconductors. Is that the one? No. Bonding in metals. No. Electrical properties? Probably. Sigma is the conductivity. I see. Oh yeah, it makes sense why it will be divided by sigma in the resistance equation then. Okay. So we have this equation. Okay, so the conductivity is equal to 100... This is actually... Okay, this is actually kind of obvious now that I'm looking about this. You know what? Yeah, okay. If it's p-doped, the holes are the majority carriers. Wait, does P stand for positive or phosphorus? It doesn't matter. We'll get there soon. Okay. And hence, if we continue to assume electromobility of 1000 squared centimeters by per volt per second, we get this. And now adding more than 6 times 10 to the 17, that is a lot. Phosphorus atoms per cubic centimeter might seem like a little phosphorus until you realize that there are almost 10 to the 24th silicon atoms in a cubic centimeter. And hence only one every 1.6 million silicon atoms must be replaced with a phosphorus atom to reduce the resistance of the sample from several tens of mega ohms down to only 1 ohm. That's... wow, that's quite a reduction. This is the real power of semiconductors. You can make dramatic changes in their electrical properties by the addition of only minute amounts of impurities. Minute is an understatement. That's a difference of how many orders of magnitude? 7. 1 in 1.6 million. Like if you have a kilogram of pure silicon, then adding just 1 milligram of phosphorus would be enough to reduce the resistance by literal tens of millions. This is incredible. This process is called doping the semiconductor. It is also one of the great challenges of the semiconductor manufacturing industry, for it is necessary to maintain fantastic levels of control of the impurities in materials in order to predict and control their electrical properties. Makes sense. Wait, how many more is that? No, we're not. Positive because N doesn't stand for boron. That makes sense. Wait, but it's P dot. Wait, so I know that there is a P and N type, but is it N doped? The smart ASMR. I don't even know what Make it's doing right now. We're just talking about semiconductors. This is cool though. Again, if this were the end of the story, we still would not have any calculator series or Agent of Doom video games, or at least they would be very big and cumbersome and unreliable because they will have to work using vacuum tubes. We now have to focus on the few empty spots in the lower, almost full band called the valence bands. Why do you have PTSD when you ask? P-doped means positive though, because you essentially catch one of the electrons and leaves behind a positive hole. Makes sense. Okay. Okay, I see. Alright. So, wait, hold on. So could you... So doping silicon... So N-doping silicon would be... In theory, you could... In theory, alright? In theory, that's important to note. In theory, you could n-dope silicon with aluminum then. Because that would mean less electrons, and so electrons would basically have to... Right? Right? I think in theory, right? Yeah, I'm certain. Yeah, we'll see. We'll see. Size the constraint for using other atoms. Which sides? There are a couple we have to worry about. They use boron. Boron? For silicon? Wait, boron. Hold on, boron. Boron is... Wait, why boron? Why boron, not aluminum? Instead of aluminum. Wait, why? Why boron? How many valence electrons the dopant atom has? Yeah, but if creating a positive, a p-doped semiconductor, if you can create it with phosphorus, because it has one more valence electrons, then shouldn't you be able to do the same thing with aluminum? I don't know, it fits better in the silicon ladders, I guess. It's chemistry, man. It's chemistry. There are 7 million reasons why this could happen. Maybe because you need reactive non-metals. Maybe because post-transition metals don't work. Maybe it's because of the electron configuration. Maybe aluminum just had... Maybe number 13 is just unlucky. We never know. Isn't all metalloids are semiconductors? Yeah, but we're talking about doped semiconductors. Because you can dope them up or down or positive, negative, you know. Okay, so I guess that's the question I'd like to answer this stream. Why boron, not aluminum? Nice question to answer, in my personal opinion. Yeah, okay. I must confess at this point that what I'm giving you is even further from the way things really work. Boy. Oh, I know why Alex is here, by the way. I know why Alex is here. Hold on. I know why Alex is here. It's because we mentioned quantum mechanics. It's a tale as old as time. If you mention quantum mechanics on stream, Alex appears. A helpful spirit to guide us through the vast and unknown seas of Libetext. Okay, hold on. Oh. Bro, did we even up? Hold on. This, yes. From some different perspective. The problem is that in order to do things right, we have to get involved in momentum phase space. This sounds fun. A lot more quantum mechanics and generally a bunch of math and concepts we don't really need in order to have some idea of how semiconductor devices work. Obviously, you need quantum mechanics to understand how transistors work, because it would be just too easy the other way. Okay, it's fine. It's fine. Okay, it's fine. What followed below is really intended as a motivation, so that you will have some feeling that what we state as results is actually reasonable. Okay, so basically all of this exposition thing we did, alright, all of the quantum mechanics research, all of the basis of chemistry is irrelevant. It's irrelevant because we're skipping over that anyway. It's fine. Okay, let's continue. This is phenomenal. I'm having fun. Boy, I'm glad I listened. You know what? Now it gets a bit complex. Now it gets a bit complex! I was about to say, before you rudely interrupted me, Alex, I was about to say that I'm glad I listened to Alex when I said that, you know, we can skip over those, because otherwise I would just... Because we're skipping over them anyway! Wait, I just remembered, if you look at the size trend, the aluminum atom is larger than silicon atom. Really? That's interesting. It's chemistry. That's chemistry moment. Radius. It really is. It really is larger. Obviously, the largest atoms are in the bottom left corner because learning about negatrons. I'm learning about semiconductors because it's easy stuff. All of this research we've done so far completely useless because we're skipping it. I'm not mad, you know. I'm just okay. Why Marvel movies keep excusing everything under quantum mechanics? No, quantum mechanics is not difficult. It's not difficult. I have to mention that. It's really not difficult. It's complex. There's a difference. The difference being that it's not actually that hard to understand why some things, how some quantum mechanical things work. It just takes a lot of time and a lot of work. The work which we're not doing here, actually. I mean, we did do some of it, and then it's completely useless because we're skipping over quantum mechanics anyway. I'm glad to have missed everything before now. Yeah, I told you it won't matter. I just don't understand the phenomenon, just say quantum mechanics. I don't know, you know what? I'm not all that mad about the quantum mechanics thing. I'm more mad about ions and how, you know, whenever in movies or video games and books, whatever, whenever, you know, they have something with a lot of energy, they always call it ion. As in, you know, I-O-N. I-O-N. This. I know I'm pronouncing like iron. It's ion. Is the work measured in electron volts? Yes, it is. Of course, this. It'd be too easy, but it's just too easy the other way. Of course, it's measured in electron volts. The difference being you made a whole video about this. I made a whole video about the basics. I made 2 videos actually. I made 2 videos about quantum mechanics. The basic one and the cool one. In my opinion, at least. I miss you learning about electron volts. What the gradient? I know. I mean, we didn't really get into electron volts all that much. We just used them. They are. You didn't really miss me learning about electron volts because remember the electricity chapter where we like derived Ohm's law, or rather where in the chapter there was the Ohm's law kind of disassembled into base units. That's basically the entire mention of electron volts. And now we just use them. You know, over there we learn about volts, we learn about electrons, that's good enough. Electron volts is really similar to... Oh wait, there was another one, there was another unit. Kilowatt hours. Oh yeah, I mean, kilowatt hours, that's such a great unit, isn't it? Kilowatt hours. I don't know if y'all have ever seen this unit. Hold on, let me just untangle my headphones and I'll show you. I don't know if y'all have seen. There's nothing like electric. I don't know. I really like. I myself really like kilowatt hours. This is a university. It's a library textbook. Kilowatt hour. It's great. It's phenomenal because it's like a unit which combines watts with time. And you know, we don't have any other units which can... We don't have anything else that would combine work with time, you know. If only we had a unit, an SI unit, which could help us. Joules because electron... Yeah. Bruh, indeed. We wish they should do this in kilowatt hours. EMP enjoyer. Mix and match formula symbols with units like it's nothing. Yeah. I mean, I myself enjoy the idea of, you know, only introducing units when it's absolutely necessary and using them kind of like vectors, you know? So basically, unit being a kind of basis vector. I don't know if you catch my drift. I like that idea. That's why, for example, mol is so absolutely idiotic, because mol, you can use mol as a scalar if you want, which actually it's cool for a base SI unit. You know, you can't use meters as scalars, you can't use the kilograms as scalars, you can't use Kelvin as scalars. You can use moles as scalars, however. So I'm a huge fan of the idea that you can use that. You should only introduce units when it's absolutely necessary, and you know, only have them as these basis vectors. And so electron watts, kilowatt hours, they're all phenomenal units which are incredibly useful. You couldn't possibly describe them in any other way. Well, 1 and I basis vectors for complex numbers. You don't see number 1. Well, yeah, but like, well, hold on. I'm not complaining about 1 because it does make, that actually makes sense. No, hold on, Alex. Hold on now. Well, hold on, the boy. No. That's different. That is different. First of all, because I already went on a rant about how using the complex plane as a coordinate system is a bad idea. We already had a whole separate discussion just about that, okay? Where I was like, I think I was arguing with Elliot. I don't know. Wait, who was I arguing with? Oh, I don't remember. It was months ago. But the point is, we already had an argument about this. How, like, in my opinion, complex plane is pretty awful when it comes to using it as a coordinate system because of the whole I squared predicament. It's great for describing rotations, awful as a coordinate system. I don't know if there exists a number system like binary or decimal which consists of the BS constant like pi, Planck's, etc. I'm pretty certain it's mathematically impossible for a system like that to exist because of the whole transcendental number debacle. Can you add the rule in the server that says never say mole? No, what if people are talking about animals? I don't wanna take away, you know. I'm not a fan of big government. You know, the big government trying to censor people talking about animals and stuff. You know, the usual. We've all been there. Is there a thing about negative heat having to do with orbital things? I watched a YouTube video once explaining negative heat. Wait, negative heat? I'm sorry for skipping over that, by the way. Negative heat? Doesn't make much sense. How can you have negative heat? Because heat is a scalar. Heat doesn't have directions. We've already been over this textbook. I like moles. I'd love to have 10 to 23rd of them in my garden. You're treading a fine line, Alex. I find the video was super weird. Yeah, I mean, it does seem weird because it doesn't really make much sense for negative heat. And let's not, you know what? Well, let's semiconductors. That's what, yeah, right. That's the thing. Here we show all the electrons in the valence or almost full band, and for simplicity show one missing electron. Remember, electrons in the valence bands are bound to the atom. They can't move far. Let's apply an electric field as shown arrow in the figure. The field will try to move the negatively charged electrons to the left, but since the band is almost completely full, the only one that can move is the right next to the empty spot. Or hole. Okay, yeah, makes sense. So yeah, this is genuinely whole as a charge carrier. Okay. You seriously need more moles. You can have more moles, alright? Because it's not a unit, they can't. Right, so electricity, that's what we're doing. Okay, cool. Are you a fan of colds, make it? No, colds are awful. That's why I would recommend you all join into my I like have a group of people who hate cults together. We call it the collective of anti-cultists, and if you want to join in, I'd recommend. wonder how many moles are in the mole. That's the problem! You can't ask a question of how many moles there are in the mole, because mole is the quantity of... You have to specify moles of what? In which case, the unit becomes pointless, because you can just skip the mole part and add a number. It's fine. Negative temperatures are 60 symbols. Huh. That number of... I mean, is that the... Negative temperatures are hot, 60 symbols. It's at the title of the video. I'm curious. Let's see. And negative temperatures are hot. Let's see. I don't get negative temperatures. 1.1 million views in 11 years. Oof, that's a lot of views.
Go with me. Okay. Don't talk to me. Just go with me.
Wait, is this? Hold on. Is this? Math with 60 symbols. Wait, isn't this? Math. Oh, what's his name? Math what? The math guy. The Bill Nye, the math guy. The who? Damn it. Yes, it is. Okay, yeah. Okay, that is. Yeah. Number file, yes, precisely. I was thinking of computer file, and I honest to Lord thought that the math computer file had math in the name for some. I don't know. Number file, yes, okay.
Show me what happens if the temperature of that is absolute zero. Thank you.
It can't be.
I know, but there we go. Now show me what happens if that is lukewarm.
Okay, yeah.
But
Alright, no.
Yeah.
Now,
Well, lukewarm would be quite fast still. And these are the periodic table videos. Hold on, Brady. Yes! Okay.
show me what happens if that is very hot. Now,
Negative temperature,
show
come on.
me what happens if that is a negative temperature.
you can't do it.
Yeah, right? Hold on. I don't wanna... Okay, Well, I'm in quite a pickle, I gotta say, because I'm really curious now to see what negative temperature is. But I can't. I have a... It's a matter of principle. Because I can't really... I don't wanna do it... I don't wanna steal content. Also, love how 60 symbols there's. You have your lambda, your phi, your psi. It's nice. Even when you're walking on. I mean, I can't watch it on stream. that's the problem. Negative temperatures. How would negative temperatures work? Below zero are hot and those above. Below absolute zero. But how could they be below absolute zero? Make it reaction? No, I'm not doing reactions. It's a matter of principle. I'm not doing reactions. That's exactly the problem. But like, how could it be? Has to do with orbitals and potential. As in, wait. Oh, wait. If thermal. Wait, hold on. If temperature could be kinetic energy of particles, then would negative temperature just be the increase in potential energy? That doesn't make much sense. Like, absolute zero has potential energy. The reactions, no, I won't do reactions, no matter what the result would be. It's a matter of principle. I don't steal content. I don't like stealing content. Anyone who should make a genius or a mentally ill person. Cool. Wikipedia. Oh, thank goodness, Alex. I should really pay Alex, honestly. Hold on. There we go. Bad money. Okay, negative thermodynamic temperature. That is, the temperature can be expressed as negative quantity of the Kelvin or Rankine scales. From temperatures expressed as number. Yeah. Negative temperature on Kelvin scale is hotter than any system with a positive temperature. If a negative temperature system and a positive temperature system come into contact, heat will flow from the negative to the positive temperature system. But what does it mean for something to have negative temperature. It's another example of population inversion in laser physics. Okay. States, however, have a maximum amount of energy that they can hold, and as they approach the maximum, their entropy actually begins to decrease. Oh, that's such an unsatisfying answer. Oh, that's such an unsatisfying answer. So this basically is like, oh, that's kind of a technicality. So it's okay. So of kinetic energies of all molecules. So I guess you need negative mass. No, Ramit. It's basically kind of going off on a technicality where like always increase their entropy. Yeah. So that's the key, I think. Right? Cannot achieve negative temperatures. So adding heat will always increase. So if adding heat decreases the entropy, so it's basically like a technicality based on the definition of temperature. Oh, that's so unsatisfying. Oh, come on. Oh, I'm disappointed. Temperature is measuring wiggles. Yeah, but in this is basically they take the definition of temperature and okay. The possibility of a decrease in entropy as energy increases requires descent to saturated entropy. This is the only possible number. Limited. However, have a maximum amount of energy that they can hold, and as they approach the maximum energy, their entropy actually begins to decrease. Okay, so it's basically how based on entropy, yeah. How would the particle jiggle backward? That's just jiggling. That's precisely the issue with temperature, right? It cannot be negative in that sense, right? Because it's an average of it's basically based on the average velocity of particles, and it doesn't really care which way the particles are going on average. And so that's why negative temperature has to be defined in a different way. Oh, I mean, honestly, it makes sense. New temperature should be wiggles per hour. I'm pretty certain this. Wait, we know it down somewhere around here. Where's temperature? There it is. That's the average translation of kinetic energy. But there. So there we go. That's temperature. That's the absolute temperature, I think. True temperature, whatever it's called. That's the equation. Where V bar is just the average root mean velocity, and well, pretty simple. We saw that on your video, there is no negative distance. Yeah, that's basically what that video was about, where, you know... what was the name of that video? It was a pan with temperature, I remember. I remember that video because Theft actually made the thumbnail for that video. Fun trivia fact for y'all. Back when I uploaded that video, it got 50 views in, I think, 3 days. Which means it got less than 10 views a day. No, wait, less than 20 views a day. In the very beginning. And only once the addition to quantum mechanics video showed up, only then. So, okay, the point is this. One thing you might be worrying about is what happens to the electrons at the end of this sample. This is one of the places where we are getting somewhat distorted views of things, because we really should be looking at momentum or wave vector space rather than real space. In that picture, they magically drop off one side and reappear on the other. This doesn't happen in real space, of course, so there is an easy way we can deal with it. A short time after we apply the electric field in situation, this one, and a little while after that, we'll have figure 3335. So this, right? Yeah. So the hole is moving around charge carrier. No, hole being the charge carrier in this case. Then electrons 3 a.m. We get a picture of what's going on. A single positive charge moving to the right, shown in the figure. Not in either view, we have the same net effect in the way it will net charge transported through the sample. In the mostly negative charge picture, we have a net electron flow, negative charge, to the left in the single positive charge picture, we have a net flow of positive charge to the right. Both give the same sign for the current. Thus, it turns out we can consider the consequences of an empty space moving through a column to motion of electron in an almost full band as being motion of positive charges moving wherever these empty spaces happen to be. We can call these charges charge carriers holes. That's what I've been saying. Ah, yeah, I'm so smart. And they too can add to the total conduction of electricity in a semiconductor. Using, oh, is that Pierce? That seems like a Greek character. Okay, I don't remember the name of that one. Greek letters, whatever. Same difference. Oh, or row. That's row. Yeah, they're not. Some of us aren't as knowledgeable. Okay, some of us need some help. I knew that, Alex. I was just looking up for other people on stream, just in case, you know, because in case someone wasn't sure. That's why I was looking up. I knew what that was. I knew that was row. Okay, I'm smart. I know. Yeah, I know math. Yeah. Anyhow, from learning about bonds yesterday to silicon doping. We skipped over a chapter. Semiconductor using rho to represent the density in, you know, centimeter cubed of spaces in the valence band, and nu E and nu H to represent the mobility of electrons and holes respectively. They are usually not the same. Good to know. We can modify equation 1.1.11 to give the conductivity when both electrons holes are present. Okay, yeah, so we have the mobility of electron holes times Q, that's Q, right? Times charge. Okay, so mobility of electron holes times the charge density. So this is basically the density. And so if this is the mobility, then this would be something like kinetic energy equivalent, something like that. Say, I love the make and mark before I get to work. I'm really glad you like it. Open muscle in the back. Listen, I'm just waiting, okay? Tefta, just let me know when, and I will, because right now I haven't stopped mentioning the charity because I'm just waiting for open muscle. I'm just waiting for the link to donate. You know what? That's it. I've gotta start talking about this on streams. I need to peer pressure you. I need to peer pressure you into getting that link. You know, that's what I need to do. So everyone, I need. If that link won't appear soon, I'll have to start peer pressure. Good luck, Wolf Tefta. That is true. Good luck, Tefta. Have fun. We won't need donations though. What was the point of... what was the point of me then? We won't need donations though. Come on. I'll be useless then. I'll contribute nothing. You know how bad that would make me feel? Hold on. Open source hardware. We need awareness. Why not both? Why not both? We need people to help with coding and engineering. We can, you know, link. No, I'm just saying that, you know, Tefta basically is borderline has a charity. I'm saying borderline has a charity because technically it is in the process. Can I talk about this on stream? I can talk about this on stream, right? I mean, yeah, it's public. Okay, Open Muscle is public. The point is, Tefta is the creator of Open Muscle. That's the charity responsible for, you know, creating open source hardware and software for prosthetics. And so what I want is I want Tefta to make a link so that people could donate to Open Muscle, because then I could add an option of donating, right, through Slice of Pie, and Slice of Pie would, and then, you know, then this would be cool, because then I know I could actually have like we could have like Slice of Pie set up for an actual charity thing. Well, that's, well, whatever. Well, I'll send some charity. The point is, I feel awful because Tefta helped me a ton, really ton. Around 90-something% of money I earned off Patreon, that's just Tefta. There's 90-something% of Patreon money is just Tefta, and I did nothing in return. So, you know. I think I'm making it for profit like I'm doing the robotics, so fine! If you're making it with open source, you can still accept donations, can't you? Right? No? Good enough for me, in my opinion. Good enough. You advertise for me for free? Yeah, but I'm advertising for nothing. I mean, I am advertising the open muscle, but I'm not, you know, it's not really having consequence. I'm doing the worthless kind of advertising. I want to do a worthful kind of advertising where it would actually bring in some worth, some value. Or money, we know. I need a charity. I want a charity, because right now, what's the point of me? I'm pointless. Money simple. See, I'm just saying, and you gotta know I love money, right? So okay, the point is, hold on, we're doing this right. How can we get a sample of semiconductor with a lot of holes in it? What if instead of phosphorus we do our silicon sample with group 3 elements such as boron? Oh, that's the end doping. Okay, so we're getting into end doping now. Sounds like an existential crisis. Make it. Money for making Patreon. No. I was actually trying to convince Tefta to completely cut off Patreon, and instead Tefta just lowered. So yeah. No. We want the opposite of giving money on Patreon when it comes to Tefta. We want. If there was an option, I would refund that money, give back, but there isn't. I want link to donate. 11 people watching film. I wonder what happened to the 5 people that left. People always leave when I start talking about charity. It's a trend. It's a trend on these live streams. Whenever I start talking about charity, they just leave. I don't know. There are some missing orbitals or places where electrons could go if they were around. This modifies our energy picture as follows in figure 3338. Now we see a set of new levels introduced by boron atoms. Located within the band gap, just a little way above the top, almost full valence bands, electrons in the valence band can be thermally excited up into these allowed levels, creating empty states or holes in the valence bands. The excited electrons are stuck at the boron atom sites, called acceptors, since they accept an electron from the valence band, hence acts as a fixed negative charges. Okay. You probably are at work like me. No. If they were no, because if they were at work, they would randomly leave throughout the stream, and everyone always leaves right when I start talking about charity. So obviously, do you mean charity or this? Because this really, I mean, this is just like what we've been talking about, except the other way, right? The opposite of this. This. So basically, right here we have an additional electron, so they have to go somewhere, so they go up. Right here we have a missing electron, so instead of, so you know, they kind of suck up the electrons. It works, that is no excuse. Yeah. Okay. A semiconductor which is doped predominantly with acceptors is called p-type. and most of electrical conduction takes place through motion of holes. Conductor which is open with donors is called N-type. Action takes place mainly through motion of electrons. So negative means electrons, positive means holes. Simple. Make it. You can promote one of my videos so I can get 180 more watch hours and sell the real mug you have digitally. Oh, that'd be cool. Oh yeah, Ted has a YouTube channel, everyone. I don't know where to promote it. I've never promoted anything like that. Hold on. Yeah. Theft has a YouTube channel, everyone. There, I'm gonna paste it into Discord. Y'all go. Where's the promotion channel? Right here. This. There. Paste it. Go watch. Go. We need 180 watch time hours. In case anyone is free. I think Tefta meant like digitally as in online. I think that's because you know real mug would suggest. He reminds me of smarter Iron Man. Cable prototypes. Oh, you could. Okay, crazy idea. You could just accept money for free. Which, you know, you could sell mugs, or you could just accept money. Money. Straight up money. Current subscribers said that's true. Alright, now what? This. On YouTube, once I get 189 watch hours, well, we're working on it, okay? You could donate on it, but I want to donate for such a fun. Okay, this. In antimaterial, we can assume that all phosphorus atoms of donors are fully ionized when they are present in the silicon structure, since the number of donors is usually much greater than native or intrinsic electron concentration. Yes, if Nd is the density of donors in the material, then N the electron concentration. I'm not dealing with moles. Number of donors is usually much greater than the native. Okay, so wait, why? Wait, in N, number of phosphorus atoms donors are fully ionized when they are present in the silicon structure. Since the number of donors is usually much greater than native, really, that would mean incredibly low resistance. Right? Or am I misunderstanding this sentence? No, number of donors is usually much greater than native, which means we have more phosphorus than silicon. Electron concentration is the density of donors in material, then N the electron concentration. Material charge is boron is present, the material is called p-type silicon, and the whole concentration is just P, roughly equal to Na, where Na is the concentration of status, and these atoms accept electrons in the balanced body. Then whichever got the higher concentration wins out. This is called compensation. Yeah, so just add that simple. Or subtract in this case, I guess. Turns out the product of electron and hole concentration material must remain constant. Mass action law, which might be familiar from chemistry, in silicon at room temperature. I'm not familiar, I haven't gotten into chemistry yet. Because if we have an n-type sample silicon with 10 to 17 donors per cubic centimeter, then N, the electron concentration is just 10 to 17, and P, hole concentration is 10 to 20th divided by 10 to 17, so 1,000th of a cubic meter. Carriers with dominant material are called majority carriers, which would be the electrons in the above example. Called minority carriers, the holes in the example, and while 10 to 3rd might not seem like much compared to 10 to 17, the presence of minority carriers is still quite important and cannot be ignored. Now that the material is endowed, then it must be that N is equal to P is equal to Ni is equal to 10 to 10 with S volume. Okay, cool. Yeah. Okay. The picture of cups of different allowed energy levels is useful for gaining a picture understanding of what is going on in a semiconductor, but becomes somewhat awkward when you want to start looking at devices which are made up of both N and P-type silicon. Thus, we will introduce one more way of describing what is going on in our material. The picture shown in figure 3339 is called a band diagram. The band diagram is just a representation of the energy as a function of position with semiconductor device. Okay. In the band diagram, positive energy for electrons is upward, whilst for holes, positive energy is downwards. That is, if an electron moves upwards, its potential energy increases, just as with normal mass in a gravitational field. Also, just as a mass will fall down if given a chance, an electron will move down a slope shown in the band diagram. On the other hand, holes gain energy by moving downward, so they have tendency to float upward if given a chance. Much like a bubble in a liquid, the line labeled EC in the figure 3339 shows the edge of the construction band. Shows the edge of the construction band, okay. Or the bottom of the lowest occupied allowed band, whilst EV is the top edge of the valence or the highest occupied band. Alright, the band gap, EG. There is no EG, but the material is obviously EC minus EV. Okay, there we go, makes sense. So we have a gap in between the highest valence and the lowest conduction, right? The dotted line labeled EF is called the Fermi level, and it tells us something about the chemical equilibrium energy of the material, and also something about the type and number of carriers in the material. More on this later, because of course we're skipping over. And there's no zero energy level on diagrams such as this. We often use either the Fermi level or one of the band edges as a reference level on the view of knowing exactly where zero energy is located. Gee whiz, okay. Energy position seems complex enough. The distance in energy. Okay. The distance in energy between the Fermi level and either EC or EV gives us information concerning density of electrons and holes in that region of the semiconductor material. The details, once again, will have to be begged on the grounds of mathematical complexity. It turns out that you can say this is that e to the power of these. I think that's e to the power of this. Okay, so n is equal to... Okay, it's fine. It's fine. We can get through this. It's easy. It's easy stuff. Simple enough. Simple as it could be. It's not difficult at all. I'm not struggling. Both NC and NV are constant that depend on the material and temperature we're talking about. Yes, but typically on the order of 10 to 19. Yes, cool. Boltzmann constant. Which means the bigger the number in the exponent, the fewer carriers we have. Because it's negative. Okay. Simple stuff. Thus, the top expression says that if we have n-type material, then the conduction band must not be too far away from the Fermi level. If we have p-type material, then the valence band must be close to the Fermi level. The closer EC gets to EF, the more electrons we have. The closer EV gets to EF, the more holes we have. Alright. Makes sense. Hi, the feeble. Kind of makes sense. Good. Neat. Good, neat. Splendid. While the conduction and valence bands are separated by a fixed band gap energy, these bands can be above or below Fermi level. Be a sample of n-type material. Yes, because EC is close to EF. If we know how heavily a sample is doped, that is, if we know what ND is, for example, the fact that N is roughly equal to ND, we can use the equation 3335 to find out how far the Fermi level is. Conduction band. Jeez, this is fun. Okay, cool. To help further in our ability to picture what's going on, please do. We will often add this to this band diagram. We will often add to this band diagram some small side circles to indicate the presence of mobile electrons and holes in the material. Note that the electrons are spread out in energy. From our CAPS picture, we know that they like to stay in the lower energy states if possible, but some will be distributed into the higher energy levels as well. What is distorted here is the scale. The band gap for silicon is 1.1 electrovolts, while the actual spread of electrons will probably only be a few tenths of an electrovolt. Not nearly as much as shown in the figure 333. The sample of p-type material, just for comparison, note that the holes increasing energy goes... For holes increasing energy goes up, goes down, not up, so the distribution is inverted from that of electrons. You can think of holes as bubbles in a glass of soda beer. So they can. Also for both n-type and p-type material, there is a few minority carriers of the opposite. Okay. So far, kind of makes sense. We are now ready to make an actual useful device. Oh yes, we sure are. Okay, let's take a piece of n-type material and a piece of p-type material and stick them together. This way we'll be making a p-n junction or a diode, which will be our first real electric device other than a simple resistor. The band diagram might look like the figure this. Okay, so we're sticking together n-type and p-type. Neat. Oh, this is fun. This is fun. I'm having fun. I'm having fun, and all is great. All is neat. All is fun. This shows the conduction and valence bands at the same energy for both p and n type. Should be drawn the constant Fermi level and Fermi level. Oh yeah, Fermi is different. That is true. Fermi energy will always be the same for everything in device system equilibrium, not the temperature. Yeah. So figure is drawn wrong. Fermi level should be the same everywhere through the device. If you draw the device band diagram again, constant Fermi level, the conduction bands will and valence bands must be at different energies as we move the device. There is no problem with this since the conduction and valence bands are drawn relative to Fermi level. So this would actually look like, and makes sense that because you know this one is close to Fermi level, this one is close to Fermi level because this is p-type, this is n-type. Now we're getting somewhere. We really are. Okay. There are still problems with this band diagram. Now we have a bunch of holes on the right and a big bunch of electrons on the left. We would expect that in the absence of forces to keep this away, they will start to spread out until the distribution is more or less equal everywhere. Makes sense. A diffusion process. Finally, we remember that a hole is just an absence of an electron, and since an electron in the conduction band can lower the system energy by falling into one of the empty hole space states, it seems likely that this will happen. This process is called recombination, because the combined hole electron recombine. That makes sense. The place where this would most likely, of course, would be right at the junction between N and P regions. Yes. Now, why don't they just cancel out? Let's see. Now, this might... Now, it might seem that this recombination effect might just go on and on until there are no carriers left in this sample. Yeah. Some alchemy, material science. Nice to meet you. Wait, you've never... Wait, have you really never met Alex? Really, people? Oh, I guess you do spend most of your time on Discord. Not really. I haven't. Really? That's bizarre. Oh, my playlist ended. Well... Let's restart. There we go. Oh, okay. Figure 3344 is more physical than what we've been looking at so far. It's a picture of the actual p-n junction showing both the holes and the electrons. We also need to put in the donors and acceptors. However, if we want to see what goes on, dot. That's the end of the sentence. The fixed meaning they can just move around. Charges of the donor and acceptor atoms are represented by simple plus and minus signs. They are arranged in a nice lattice-like arrangement to remind us that they are stuck in the silicon crystal lattice. In reality, however, even though they are stuck in the crystal lattice, there are so few of them combined the silicon atoms that their distribution will be quite random. For removable holes and electrons, we will stay with little circles and charge signs on them. Okay. Now, still, why don't they recombine? Phenomenal question. We will now have to allow some of the holes and electrons, again near the junction, to recombine. Remember, when an electron and hole recombine, they both are annihilated and disappear. This makes sense because hole is just an absence of an electron. So if you take an absence of an electron and an electron, you just end up with, well, an electron. But not an additional electron, only an electron. Note that this process conserves charge and we could calculate the momentum as well. There's obviously some energy lost, but this will simply show up as vibrations or heat within the crystal lattice, or in the case of an LED, light emitting diode, as light emitted from the device. See, already we know enough about semiconductors to understand somewhat how an actual device works. Okay, light coming from an LED is simply the energy which is released when an electron and hole recombine. We will take a look at this in more detail later. Let's allow some recombination to... Okay, but why isn't recombining all the way? People made them once, but they were funny with coal. Really? Oof. What's the hole? It's when lack of an electron. But why isn't it recombining all the way? Also, I don't like how this is divided into two parts. Never a good sign. If you look closely at these pictures, you will notice something. As we remove more and more electrons in the holes, we are starting to uncover the fixed charges associated with the donors and acceptors. We are making what is known as depletion region, so named because it is depleted of mobile carriers, holes and electrons. The uncovered net charge in the depletion region is separated with negative charge in the P region and positive charge in the N region. What will such a charge separation give rise to? Why, an electric field, of course. Which way will the field point? The electric field, which arises from separation of charges, always comes from the positive charge towards the negative charge. But why don't they just keep on recombining? That's what I'm curious about. What effect will this field have on our device? It will have the tendency to push the holes back into the P region and the electrons into the N region. Oh, so it's because of the field. Oh, right. That makes sense, kind of. Okay, I feel like I'm just repeating myself. This is just 2 hours of making repeating. So, hold on, how long have I been streaming for? Hour and a half, yes, almost 2 hours of me just repeating myself. Every single live stream is the same. Oh, this makes sense. Kind of. Huh. And just this on loop. This is just what we need to counteract the recombination that's been going on and hopefully bring it to a stop. Okay, cool. So that is actually what stops recombination. Now trying to think through what effect this field could have on our energy band diagram. The band diagram is for electrons, so if an electron moves from the right-hand side of the device, the N region, towards the left-hand side, the P region, it will have to move through an electric field which is opposing its motion. But our band diagram has a sudden shift or discontinuity in the conduction in valence bands. A moving electron can't suddenly change kinetic energy. The band must be continuous across the p-n junction. We can fix this by making a smoother connection between two bands. Find the exact function for this later, for a later course. So is that why electricity can flow only one way through a diode? Because wait, but wouldn't that mean that electricity can actually go the other way through a diode if you have enough energy to counteract the field? Wait, wouldn't this mean that if you apply enough voltage to counteract the field, you could actually go the other way? So when the standard recombining the field of the underlying ions becomes more relevant and eventually stops them from recombining. Yes. Okay, wait. So here's the thing. Given that we're talking about the diode, from the very beginning it was obvious that the conclusion will be you would probably destroy the diode first. But it is possible. Okay, here's the cool part, right? Here's the cool part. Given that we're talking about the diodes, it was obvious from the very beginning that this would be the conclusion, right? You can only go one way. But the cool bit is that I had no idea it was actually possible to go the other way. So we actually know how the diode works. The way it stops the... So it's basically eliminating the potential with the electric field. Because... Well, not eliminating. Good job so far, make it? I have no idea. I mean, we're getting somewhere, certainly. Diagram, yeah, okay. Electron has to do some work. In other words, the potential energy for the electron must go up. There is a shift in potential energy as electrons move from the right to left across the junction. Okay. So in other words, we have this, which is based on the ions, underlying ions, but this current is this field is moving electrons to the left. Not electrons, holes. This is moving holes, positive charges, to the left. So negative charges stay on the right. And that's why we still have this separation. Alright, this makes a lot of sense. That's a lot of equation, but okay. The shift of the bands, which is just the different potential in this location of the Fermi level in the N region and the Fermi level in the P region, is called built-in potential. Makes sense, that would be VBI is potential built-in. This built-in potential keeps the majority of holes in the P region and electrons in the N region, provides a potential barrier which prevents current flow across the junction. On the band diagram, we have to multiply the built-in potential by the charge of an electron Q so that we can represent the shift in energy in terms of electron volts, the unit of potential energy used in the band diagrams. How big is the built-in potential? This is not too hard to figure out. Let's look at figure 3352 a little more carefully. Is the above one? It is. Okay. Remember, we know from equation 137 that since... That's way back in the... Okay, that since n is equal to nd... Oh no, that's the previous one. Okay, in the n region, and p is equal to na, in the p region we can rate the distance of the Fermi level from EC and EF by this. So, that's natural log. Okay. So, basically, KT, Boltzmann... Okay. Up. Go. That's the only temperature thing we have. Why natural log? Natural log. Natural log because of the previous equations with e to the power. That's why. That's why natural log. Let me get those equations quick. Where are the equations? Even further back. There we go. Make it. How do you get smarter? I don't. I just pretend. It's from definition of carry density. You mean this one? That would make sense. Natural log. Alright, so. Wait, no, that wouldn't make sense with natural log. I take it back. Yes, it would make sense. What am I talking about? Hold on. What am I talking about? What am I doing? Where am I? Who am I? What is math? So next few equations, I believe. The literal next equation, actually. Fact that n, yes, but this is just this equation, right? Like this is based on this equation. So EC minus EF is equal to KT natural log of NC and D. Wait, NC, hold on, NC, oh, this again. NC and D. Okay. Doesn't make sense. It's fine. You know what, let's just, I believe, you know what, I trust the author of this textbook. It's fine. And this, just for the P, we have one for the N, one for the P, makes sense. Look at figure 3, look at figure 3352 and see if you can agree that. And then this equation. Connection versus valence band numbers. Yeah, but I just, the natural log just makes, whenever I do math, I just like to break up things for my tiny little brain, so so my tiny little brain won't get overwhelmed. And it's having a real hard time with this natural log in there. I know why this natural log is there, because of this sucker. It's not making it easy. Okay. So QVBI. So VBI is the built-in potential and Q is the charge. So let's break it down. It's fine. We're not in a rush. Let's break it down. Simple as it could. Let's see. We got to understand what this means exactly. So we have the VBI, so the built-in potential, times charge, which is equal to EG minus EC minus EF minus EF minus EV. First, let's understand this equation all by itself. So, there's this. This is from this right here. So on the band diagram, we have to multiply the built-in potential VBI by the charge of an electron Q so that we can represent this shift in energy in terms of electron volts, unit of potential energy used in band diagrams. It explains literally what this means. Now, and why we multiply it by charge. Okay, now this would be equal to, and once again, let's break it down. We have EC minus EF, which is the difference in the Fermi level and the, where is it? We need another, we need the other graphic. This right here. So this is the difference in the conduction band and the Fermi level, and this is the difference in the Fermi level and the valence band. The reason being that if we go back even more, wait, I recognize those letters. Okay, so if we go back even more, then there was a cool fact, a cool fun fact right around here, that the distance in energy between Fermi level and either EC or EV gives us information concerning density of electrons and holes in that region of semiconductor material. These once again will have to be backed off the grounds of mathematical complexity, and turns out you can say, we don't care about this. Too long, didn't read. The point is, these differences tell us if tell us the density of electrons and holes. So this one, wait, which one the closest to where? There's some information about that. If we're gonna talk about robotics, I don't know. Robotics is more like a consequence of what we're doing here. So, WP 1019, yeah. But the closest to which one that gives us what, how and where? Who am I? It's mostly coding, and coding is very boring to watch, at least. At room temperature KT. Wait, no. What am I looking for? I'm looking for this. The closer EC, there we go. That's the sentence I'm looking for. The closer EC gets to EF, the more electrons we have. So the greater, well, the closer EC gets to EF, which means EC minus EF gives us this distance, which means the smaller EC minus EF, we're getting somewhere. Okay, the smaller EC minus EF, the more electrons we have. The closer EV gets to EF. So in this case we're going the other way. The smaller this one, EF minus EV, the more holes we have. Okay, okay. Alright. Sick. Cool. What's E? G, what's the third one? What's this one? What's that one doing there? Okay, so it's not no, there we go. Band gap. Okay, so this is the band gap energy. What? Hold on. Material is obviously EC minus EV. Oh, so okay, so this one. Yeah. So this one is EC minus EV. Makes sense. So this distance, the gap between. Okay. So now this, so the band gap minus the band gap between the Fermi and conductive minus the band gap between the Fermi and valence. Wait, doesn't make sense. Shouldn't this be equal to 0? Wait, shouldn't this be equal to 0 then? If, like, geometrically, if this is this distance, so this, okay, hold on, let me just do it in Paint. That's what I don't get. If we take this, right? Then wouldn't it be this distance minus this distance minus this distance? Wouldn't that be just 0? Alright, which is equal to, and then we just turn it into a natural log, where the ND and NA are doping densities and NNP in the NNP regions respectively. Give me a second. So, controversial question. How many dimensions do you think there exist? What do you mean controversial? Doesn't know how the, not precise, not exactly. No, that's not how dimensions work. Does Ali have a YouTube channel? No. No. Ali's not that not one that I'm aware of. Okay, the main thing which holds me back now is I don't get why this wouldn't be just equal to 0 always. Which is funny because for this to be equal to 0, this would have to be equal to E. Right? Yeah. No wait, this would have to be equal to 1. Which means the ratio between the doping density of the wait no you know what, let's no, this is this is equal to 0. Minus this. So this as a plus. Minus this. So this as a plus. Right? No. I'm not crazy. So this would be equal to C minus C. These two cancel out. Which would be equal to negative V plus V. These two cancel out. Which would be equal to positive EF, negative F. That's 0. VBI and E both charge 1 electron and they cancel out, making... Why? So, this can't be equal to EC minus EV. It just can't. Has to be equal to something else. But what? No idea. Alright. Non-converse. How big would the building potential be in this case? No, I just don't get what EG is. That's what doesn't make more sense to me. Okay. The point is, now let's take a look at what happens when you apply external voltage to this junction. First, we need some conventions. Making connections to the device using contacts, which we show as crosshatch blocks. Ah. You know what? I feel like I'm gonna leave it for now. We'll have some more streaming later on. Oh, I need a break. I can't. I just can't. I can't. I need a break. So I suppose we'll end it for now. We'll come back later on. And I suppose for now will be it. Everyone left anyway, so it's fine. For now, that'll be it. Thank you everyone so much for watching. And have a great day. Bye.